Right. I'll put this on.
Hey.
I'll just. Yeah. Okay. So, I'll just. Yes, begin talking. Yeah.
All right, guys. Thanks. Thank you all for coming to the first PhySU talk in this semester. We have Professor Curtin today.
Yeah.
I will just make a brief kind of introduction, like aside before we start. We will also have a PhySU colloquium about an hour after this talk at 5 p.m. in this same room. We'll also come to that. Thank you. And now I guess Danny, go ahead.
I was gonna say. Anyway, yeah. So welcome to first PhySU talk of the semester, the second one in the year. And well, it's with Professor David Curtin in theoretical high energy physics. And so he went to high school in Germany and Australia. He completed his undergraduate education in Sydney and in Melbourne. And then he moved to the United States for his PhD at Cornell and postdocs at Stony Brook and UMD before coming to Toronto as faculty member with the Circle HED group. During this talk, he will describe some aspects of his background and motivations for getting into physics, some recent research activities he's most excited about, and directions on the particle physics, and some personal lessons and experiences that might help out you undergraduate researchers at the start of your careers. So yeah, have fun and take it away.
Thank you very much, and thank you for the invitation. This is kind of a new one for me. So I'll do my best to be useful. So basically, it's exactly like you guys heard. I was asked to cover 3 topics. So for the sake of, I always find it's easy to get lost in talks in sort of detailed statements, whether those detailed statements are technical or if they're just narrative. So let me kind of write those 3 areas down, and then I'm going to sort of just try and say something useful in each one. So the 3 things I was asked to talk about are personal journey, yes. So personal journey into physics. The second one is research interests and current research. And then the third one is tips for students studying physics. And getting into research. So I'm just going to keep it here so that we can slightly orient ourselves. Is this okay?
Yeah.
I will be over there as well at some point.
Yeah, that's fine. I'll like move it around.
I will not be writing all that many important things.
Oh, okay.
To be honest, this is really just very rough to keep the table of content of the talk kind of. So it's always a slightly awkward thing to be asked about your background and personal journey into physics. And one of the things I ask myself when I try and think about that question is, what can I tell you that might be useful to you? Okay, I could, we could imagine we're having a beer and I'm just telling you guys what brought me here, and that's fine. But I kind of want to orient itself with what can you guys maybe use? Okay. So, I'm sorry, this is way too close to my chin. It's tickling me every time I look down. Okay, is this still okay? Okay. So, so let me just start with one. So this was a little bit of a head scratcher for me in some ways, because basically, I think my story is of limited usefulness to most people, because in most ways, I precisely hew to the academic stereotypes and embedded privilege of existing structure, like almost to a T. So whatever story I might be able to tell you will help some of you, be not super helpful for many of you. right? And it's also not a unique or interesting story. But even so, I think there's a couple of things that I might tell you. So, you know, my own family background, for what it's worth, is not really scientific. Both of my parents were artists. They were singers. And for what it's worth, often struggling for money, but to be honest, mildly by choice. So it was, you know, not real lack of privilege. I grew up, my father was a lawyer who became an opera singer. And my father's father was a PhD economics official of the Australian government. So I was very familiar with the academic track. Broadly speaking, I knew that if you want to get deep into something, a PhD is a good way to go. From a very young age, that was a career track that I knew was available. So for what that's worth. Furthermore, and this is unusual even among physicists, but unusual in the direction that goes away from usefulness for most people, is that I knew what I wanted to be when I was roughly 8 years old, because one of my most significant core memories is like reading one of those kiddie astronomy books and being very fascinated by how the sun works and things like this. And even many of the best physicists in the world and people that are way more famous than me and all these kinds of things, like my favorite example is Raman Sundaram, who is this like one of the gods of theoretical physics today. And like in grad school and throughout postdoc, he was this like guitar playing slacker who like almost went into economics because he couldn't get a job or whatever, you know. So like this is not at all required for later success. So I really don't want to dwell on that. And also, it's not something that you can change now if that isn't you, right? So again, that's not a useful detail. But for what it's, so I have a lot of non-academic and academic privilege in that regard. And my story is therefore of limited usefulness. But for what it's worth, as someone on this fairly standard trajectory, I think I can still make a few useful observations that, you know, some useful observation. And useful here being very specifically to you guys as undergraduates, right? So, you know, 1A, okay, and I'll talk about this in a little bit. I'm going to sort of validate by specific example the extreme realness of academic privilege. I don't know how to spell privilege. There's an E in there, I think. Doesn't matter. I'm going to sort of give an end stage view of what actually I think matters for succeeding in scientific research. And 3, I'm going to report on some practical realities of a research career, even if everything works out quote unquote perfectly, okay? Okay, so so let me start with point 1. So now I think we have to. And again, I'm not actually going to write all that much. I'm just writing the table of content, right? But so as was already mentioned, sort of my career path as far as relevant for grad school was Cornell PhD. And then I did postdocs at Stony Brook and Maryland. And then I came to Toronto. For what it's worth, so, and again, let me be like extremely explicit, right? On the log scale of academic, let me call it academic privilege or academic pedigree, this right here is whatever, MIT, goes to Harvard, goes to Stanford, with faculty at, I don't know what's left. Princeton, very good, thank you. Okay, and especially within particle theory, so Stony Brook, you might not be super impressed by it, but Stony Brook actually contains the C. N. Yang Institute for Theoretical Physics, which is like the birthplace of the QCD jet. C. N. Yang was one of the people that made many fundamental discoveries. It's independently funded generously. It's like actually a really, really, really strong place within particle theory. And UMD contains Raman Sundram and other people. Raman Sundram being the inventor of what are called Randall-Sundram models. Those are a class of particle theory models, which is essentially one of the most important frameworks for those of you who are in the know. Addressing the hierarchy problem without supersymmetry doesn't really matter. The point is, he's a very, very, very big important person, and he is someone that helped me a great deal in my career. Okay, so Stony Brook and Maryland are very, very fine places a priori. They're not superficially on this level, but again, there's things that elevate them massively within particle theory in particular, and that places me roughly here, with this tiny distance called epsilon. Okay, right? So let's do a Taylor expansion around epsilon equals 0. Okay. Often in physics, when you want to study a really complicated system and you don't know all the details, a little Taylor expansion, a perturbative analysis is helpful, right? So, I'm not trying to harp on this too much, and this is something that I occasionally spoke about with my friends who have similar tracks, like academia is so intensely hierarchical, obsessed with reputation and pedigree, and obsessed with prestige, right? That this little tiny absolutely epsilonic epsilon was fiercely detectable, right? So of course, if you are somewhere here or somewhere here, it'll be extremely detectable, right? And the way in which it manifests is that I would know other graduate students who basically did roughly this, and they were just around all the people that had all the money, that there was some cool idea that the advisor had, and the grad student got 4 papers out of it because they were around, right? And then by comparison, in other places you do a project here, project there, still extremely good, extremely no worries at all, right? Like top 2% as opposed to top 1%. But even that difference was extremely noticeable. Not to cry about it, that's not the point. But the point of this statement is to extremely validate, right, any feeling that you have that the system is mildly rigged, okay? Like it 100 million% is, okay? And this stuff matters a lot. At the beginning more than later, but the beginning matters a lot, right? So at the beginning of a career, this matters a lot because it sets up certain opportunities, and and that's just the reality, right? If you make it through the beginning, it matters less and less. But that's kind of true of any of these initial disadvantages, right? Like someone who grows up poor and then becomes a millionaire, yeah, fine, then they're a millionaire, right? Like at that point, it stops mattering as much, right? So it's kind of a very simple, not a deep statement, but I just want to validate that this is completely real. So any feelings that you have about anxiety or imposter syndrome or any of those things, they're real, and there's a reason why they're real and they're valid, and there's a reason why they're a mainstay of academia, even if you're in this very top zone. By the way, U of T undergrad up to whatever is very close to up here, right? Like it's by being at U of T, you're very close to here, right? Just to be clear, right? Like it goes way down, okay? So, that's kind of my very, very modest point, but it's also meant to be mildly encouraging because, as much as I want to emotionally provide comfort by telling you that you're not crazy by feeling that this is happening, I also want to point out that I've been, when I was in grad school, I was very intimidated by the grad students that I know of who are all the way up here. And then I meet them, and then I meet almost all of them. Every now and then you meet someone, you're like, okay. But I met most of them at conferences or collaborated with them, and they ain't all that. They're just human. Like there were things they had a good idea. There's things where I had a good idea. There's things where I corrected them or I thought of something they didn't, or vice versa, right? Like it is extremely much more level than this crazy logarithmic scale suggests. So the positive aspect that I want to convey to you is the feelings that you're having are real about how the system works and the ways in which it's unfair. But if you are ever in a situation where you can show what you're worth, right? If you ever have an opportunity to prove yourself, that opportunity is real too, right? And if you meet some of these people that seem very intimidating, they make mistakes like everyone else. They make serious errors. They miss things. You can have ideas that they haven't had, even though it seems obvious to you, or it seems like they should have been smart enough to think of it, right? And that's deeply, deeply true. And I think that's something that you've got to internalize to like get the confidence to think of, to even do any of this, right? So that's kind of my sort of 0th order point about that. For the sake of pretending that this is a lecture, any questions? I mean, it's fine, we can chat. Like, this is not super formal, like these are my notes. Although those of you who take my classes know that these are also my real notes. I can also just move on, but interrupt me anytime, honestly, right? Like, this is not a super carefully thought out talk. I'll just pause for 10 seconds, just in case someone wants to ask. The information content isn't huge, right? So it's okay if I just keep going. All right. So, so the end stage view on what matters, okay? And again, this is a little similar to all this business. There's a phrase that I think is really helpful to some extent, which is technical genius is cheap. I'm going to put extra quotes around cheap, right? Obviously, not to discount technical genius. In sufficiently high quantities, any amount of genius is qualitatively insane, okay? Not insane as in mentally ill, you know what I mean, right? Cheap in the sense that, you know, it used to be that if you were technically reasonably good and you knew the right people, you do a PhD in one of the 20 places that mattered in North America, and then you just had a job afterwards. Unbelievable, like unimaginable, yeah? Now, the system is so much more accessible than it used to be. And by the way, there's all kinds of fun stories about how, like, this level of academic privilege is already a million times better than it used to be. Do you guys know about preprints? Okay, unscheduled side note, excellent. Do you guys know about preprints, like Archive, the Archive preprint servers, or medRxiv, or bioRxiv, or these various things? And it's great, right? Like, papers come out, boom, here's the paper. Even before peer review, you get to look at it, yeah? It's free, yada, yada, right? You get to see it every morning on your phone, if you want to. And, you know, do you guys know how that started? Does anyone know how the preprint started? Oh, no, no, no. Way basic. Here's how preprints looked in the olden days, prior to the 80s. There were 20 institutions that were friends and that mattered. And every time one of them wrote a cool paper, they had their secretaries write it up on carbon copy on the typewriter, and they took the primary copy and they sent it to the publishers. They took the carbon copy, put it through the Xerox machine, okay, made 20 copies, put it in envelopes, 19 envelopes, and sent it to their 19 university department friends. Those preprints were received in the mail every day by another secretary who would take them out and attach them to a thingy in the wall, and there would be a stand like a newspaper every morning, and the professors would come in from their 30 minutes a week teaching loads, and they would, oh, look, this is new papers, and they would just kind of leaf through the papers that were delivered by mail that they and only they had access to because they were one of the 20 institutions on these mailing lists. So if you were not at an institution that got that piece of mail, you were a year behind on everything, right? Insane, yeah? So no wonder the guys that did their PhD there got jobs right away. They were the only ones that knew what was going on. So in the 80s or 90s, I forget, someone had the bright idea that, you know, by the time people were writing their papers electronically, which I guess was the early 90s, LaTeX and compilers and PDFs, they were like, hey, let's put these on a server. And a bunch of universities like quasi-anarchically organized, and it totally changed scientific publishing. And it started, I think it did start with theoretical physics. I mean, I'm not saying we invented the internet and preprints, but we did. But it's true. And, you know, so now, no matter what university you're at, you're as up to date, right, as someone at MIT or Princeton or Harvard, right? That is a huge deal, yeah? Anyways, Oh, good, yeah, good. So the reason I got onto this, okay, is, back in the day when you limit the supply of PhDs so severely by this artificial system of scarcity, yeah, if you can do some basic calculations, you got a job waiting for you. Now, it's much more open, that is excellent, but it does mean that it's incredibly more competitive than it was 50 years ago, unimaginably so, more competitive than it was 10 years ago, okay? And there's a lot of clever people who are technically very good, right? And this is just sort of general, like, any one of you has access to better material to learn than anyone else had 50 years ago. You can look at YouTube tutorials if you're stuck on some integral, blah, 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 right? Like, there is a degree to which technical competence is easier to acquire, right? And there's greater access and so on. So what it means is that by the time you get into grad school and beyond, there's a lot of people who are technically brilliant, yeah? And absolutely, there is a minimum requirement. And I mean, I'm a theorist, so to me, this is maybe theoretical or academic or mathematical, but whatever field you're in, right? There's a minimum technical requirement where if you can't do it, you just come to the job, right? But once you're past that requirement, I would argue, and this is nothing super new again, but rather than obsessing to acquire an extra 10% of this, right? Or for that matter, being very intimidated by someone who you see who might have an extra 10% of this, right? Two sides of the same coin. What will get you unbelievably more mileage as a scientist is basically, and I mean, this sounds, I don't know if this sounds completely cliched, but there are things beyond mere technical ability that will get you, that will distinguish you. And so it is really true. Creativity, perspective, communication, big picture thinking. Right? And I mean, this sounds like some, get rich quick, like be your own boss with 10 hours a week, like seminar, but it's really deeply true, right? If you have two scientists, let's say two physicists, and they're both super technically excellent, but one of them is 10% better unambiguously. But that person that's 10% better unambiguously never talks to people and, whatever, right? And like gets obsessed with their fucking thing that nobody cares about anymore, right? That other person will be more successful. That other person will have a job when the other one might not by the time the next applications roll around, right? So this is meant to really imbue in you, like, look, you absolutely need to build whatever the technical requirements of your chosen field are, right? Like, and this doesn't come easy to anybody. I'm saying technical genius is cheap, but let me not loop it around. Like, this doesn't come easy to anybody. Like, I remember when I was an undergrad and I had some physics course, and the physics problems were so hard, the only way I got good is by doing every single problem in the book. Every single one. 500 pages of the book, I did every single problem. Because that's the only way to get really fucking good. It didn't come naturally, right? I'm not saying everyone has to do that necessarily. I'm a particle theorist. Our math problems are a little on the gnarly side, okay? And it was hurting my brain. But the point is that, whatever your version of that is, it is a very healthy thing. You need to build that solid foundation. You absolutely do. I don't mean to discount that. But once you have that foundation and you're operating as a scientist, look around and see the brilliant technical people who don't stick their head out of the sand and see if their problem still matters. Who get stuck in something, who don't know why their problem matters in the first place. They get attracted to the process, and they can't tell you why it matters. Or they work in silence and never tell anybody what they're doing, or they don't communicate why their shit matters. They know that it matters, but they can't communicate it, and therefore nobody jumps on board, nobody multiplies, nobody exponentiates, and they're stuck in some little niche somewhere. Yeah? Or they're just so fundamentally unpleasant that nobody wants to talk to them. That happens a lot. Shocker, I know, but anyway. So communication massively matters. As like, as cliched as it might sound, it really, once you get past grad school, technical genius is fairly cheap. essentially anyone that you run into at the postdoc level, you can assume that they can do the job in the technical sense. And it roughly ceases to matter at that level. Like you'll occasionally meet someone who doesn't know shit and their reputation tanks really quickly. They're like, oh, yeah. But everyone at that level can do the job, can do the thing, whatever it is. Yeah. And it's these things that matter more. That shouldn't mean that you should not build up this at this stage. You're still too little. Okay. You still need to build this. Okay. But this is sort of this is going to be a little bit of a segue for the tips that matter for getting into research. So I'll come back to that in a little bit. Before I move on to practical realities, for what it's worth, any questions? Or is this all pretty easy? Right. Not observation from someone. So fair enough. So I think all of this is a subset of big picture thinking, right? Of just forcing your head out of your sand hole, right? And try and actually think about why is it that you're doing what you're doing? And that's a super hard question. And if you have a simple answer, it's probably the wrong one, because it's one that might be understandable to your lab mate, right? Like, oh, why are you isolating this compound? Oh, obviously, we'd like to know the reactivity of this salt or whatever. It's like, oh, yeah, of course. And like the person in the next lab over has no idea why that matters. So you explain it again to the person in the next lab, and you explain it again to the person in a different department. You have to be able to explain why what you do matters to your advisor, to your lab mate, someone in the adjacent specialty, to someone in a different field, to your mom and dad. Like, I'm not kidding. If what you're doing is worth doing, it's expressible at every level why it's worth doing. That's a really useful exercise. I myself like telling stories and like things like this, so I do this. You get a few beers into me, I don't stop. But the point is that I do think it's a useful exercise, and it basically kind of like, it'll help catalyze these things to some extent, right? As far as creativity is concerned, like, I don't fucking know. If I knew, do you think I'd be talking to you guys? Come on, what the fuck? Like, right? But you have to trust that you develop the stuff organically to some extent. But if you know that it matters, you will be able to detect teachable moments in your experiences. You'll be able to be like, oh man, what that person did was awesome, right? Like I will often read a paper and be like, oh, that's so fucking smart, but not because it's a clever integral or whatever, but it's like such a cool, weird, awesome idea. A person that I admire greatly, Professor Mariangela Lasanti at Princeton. She's a collaborator and a friend, and awesome. And she's like, I mean, apart from being brilliant, she has all this down, right? So she recently put out a paper where, hey, there's these axion fields, they're hypothetical fields that could be permeating space. What if neutron stars, because they're rotating with magnetic fields, what if they excited those axion fields and sent them to us? And it turns out the math is not that hard, because people have been playing with like axions being created in magnetic fields and blah, 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 right? So like, it's a paper where technically it's like, yeah, I can understand that in like a half hour of glancing through it if I have some experience. I'm not saying you should go read this paper and feel bad about yourself if you don't, okay? But the idea is so fucking sick. It's like, oh, any axion that's below some certain mass, I shouldn't actually be looking for it as a dark matter candidate. I should be looking for it because it's produced by pulsars with a known rotational frequency that I can measure with the radio telescope. So I know that I should be looking for this like frequency spike in my like whatever, in my like axion conversion chamber. So like, awesome, right? Like I'll see a paper like that and be like, oh, that's so fucking awesome. And it's usually not because it's technically slick. Sometimes, but very rarely actually. Okay? Sometimes because of technical stuff, right? But so the point is you notice that and you can cultivate a taste in those things. And then you eventually be like, if you have a little idea of something like, oh, maybe this is awesome. Yeah. So developing good taste comes with that. And what is taste? I don't know. Ask your advisor. Okay. More questions? Cool. I'm going to just wipe this because I want this table of content. Actually, I can just do it up here. So some practical realities. it's very likely you'll have to leave your family, right? Basically, so myself, I lived in Australia as an undergrad, and Australia, I mean, it's a very nice country, but in terms of, it's 20 million people, and in terms of particle theory, they, back then especially, they had like University of Melbourne and a few other places, but they were very limited in the opportunities available for particle theory, so I applied to go to the States, right? And like a month before I left, my father died, and I had to just go and leave my mom behind all by herself. And if I didn't do that, I wouldn't be a physicist. And that sucks fucking balls, right? It's the worst. And it is extremely unlikely that you will have any control about where you go, right? It is very, very healthy to leave your undergrad institution for your PhD. You don't have to. It's completely fine if you don't, but if you do, you get a little bit more perspective. Of course you would. You go to a different place, right? But if you have the perfect setup here, then you can say that's fine. Like, I'm not saying, obsessively leave, right? But, it is a good thing to go around, see different ideas. Anything that I tell you, someone else will tell you something different. And if you listen to 10 people, then you start building up a picture, right? Like, so you have to go out of your shell. But it means you're probably going to have to leave wherever you were born. It's very unlikely that you can control where you are. You're going to have to move around a lot. And that means that grad school was a period of relative stability of 5 years, but you're working hard and, whatever. And then postdocs, 3 years, move every 3 years. And postdoc is workaholic central. And like, you build up some local connections, but it's a kind of, if you care about building up a family, about building up a community, that's hard to do on this path. And that's part of the reason why it's exclusionary, right? Like, if my mom was sick, or if I had family care, my mom, if I had explicit family care obligations regarding my family, I wouldn't have been able to do that. Or it would have been much, 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 much harder, right? I was able to do it because things were possible. So this is the reality. And if you don't do that, it's very, 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 very hard to succeed. Okay? You move around a lot, you don't choose where you live. There's something physicists call the two-body problem. I'm sure you've heard of it. This is what we call a very funny joke. Because you guys probably know in classical mechanics, the three-body problem, analytically unsolvable. Yeah? The two-body problem, it's so solvable, but not this one, ha 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 ha, very funny. This is referring to the difficulty of two partners with a career. I know, outrageous, yeah? But if one or both of you, or God save, if it's both of you who are academics, you're going to be doing years of long distance. So don't date scientists. I am joking. My wife is a physical chemist. But we did 3.5 years of long distance. I met her in New York. She was in the lab at NYU. I was at Stony Brook. And I lived in New York City because I couldn't fucking deal with small student towns anymore. And we met in New York City. And we were doing long distance for, for 3.5 years. And and we had it super easy because Washington is like a bus ride from New York. That's where I was from Maryland. So I took a bus ride. One of us took a bus ride every weekend. She got car sick, so it was me. It's fine. And then she moved to Chicago for a job at a pharma company because that's what chemists can do. They can get jobs in industry. It's fucking amazing. Like, if you guys are certain kinds of physicists, you too can get a job in industry. A lot of things are better that way. But if you're stuck in academia, so at least my wife was able to get a job but not every place constructs pharmaceuticals that use weakly interacting large molecule crystals and so on, right? So again, very specialized. So she lived in Chicago. I lived in Washington for 3 years. I flew mostly me. No, but because as a postdoc, you control your time. As a theoretical postdoc, you can work on the plane. As a lab physicist, you cannot mix chemicals on the plane. They frown on that. Okay, so I flew so much that I developed a fear of flying because I'm very. You may have noticed, but I'm pretty tall. So when I sit in an airplane, the other seats are here, and I can just see the end of the airplane. So I have an extremely accurate read on the rotational moment of the plane as it lands in Chicago, which is a very windy airport. So I developed panic attacks from flying too much, and then I got over that. But so no big deal in the scheme of things. But 3 is a long distance. That sucks, right? That's hard. And mental health is going to be a big concern. And I say that for the obvious reasons, but also specifically academia and most science jobs, you can pour every ounce of productive capacity into them. It is a never-ending sink, right? Never-ending. And you need to figure out how to exist sustainably in that space. As a postdoc, and I guess I'm going to emphasize that when I get back to tips, but as a postdoc, I the first 6 months of being a postdoc, it was oh, I'm a big boy now. I have to publish 4 papers a year as opposed to 1 every year, and all these things. So I worked myself into a complete nervous breakdown 6 months into my first postdoc, and then I kind of took a breather and I was okay, let's run a marathon and not a sprint, all right? But even so, the amount of stuff that I worked as a postdoc is barely imaginable to me now. I couldn't do it in any way, shape, or form. I've gotten too comfortable. And I'm not saying you necessarily have to do that, but it's easier. Your chances are greater if you do. But to some extent, you can work so much that you make yourself stupid. I want to be very clear on that, right? If you do this wrong, even if you're some Nietzschean Übermensch science maximizer, yeah, you can work so much that you make yourself fucking useless. And that was the place that I ended up in 5 months into my postdoc, where you try and work so much that you become measurably dumb, and then you stop, and then you take a breather, and you figure out in 2 minutes what you tiredly, exhaustedly banged your head against for the night or something, right? If you pull all-nighters, you've learned this lesson the incorrect way, right? You generally don't want to pull all-nighters, right? You're going to get too old by the time you're a postdoc. You can probably barely do it now. I remember being 20. It was fun. But you should not be doing all-nighters in your job, and you certainly shouldn't be doing it on a regular. You will not make it. Or you will become some husk of a person. And those guys are out there. They're walking wounded. It's really not cool. So you have to take this very, very seriously. You have to find balance to the extent that you can, and that is super difficult and field dependent. But that is what it is. That's all I have to say about point number 1. Points number 2 and 3 will be shorter. Questions? How much what, sorry?
Given how much you get paid in PhD.
Right. I left. Oh, sorry. The question is how finance? And the answer is that I was credit card debt free for the first time 3 months into my faculty job. Because I had a mom in Australia, so every time I fly back, fly back and forth, it's $3,000. And I lived in New York on a postdoc salary, which means that it's going to be very difficult. I would recommend you get comfortable having roommates until you're 35. I'm not fucking kidding. You have to like science that much, unless you live in some college town out in the cornfields, in which case life is fine. But I happen to do my postdocs in Washington and DC, which are very affordable, and therefore I just had roommates. My house in DC, oh man, I had the best house in DC. I paid $400 a month for a room in the middle of downtown DC. The only downside was that the back half of the house was structurally unsound. My roommate had rabbits that shat everywhere. And we were just swarming with mice. But $400? Come on. So yeah, that was my second postdoc. So I believe that was 2011 to 2014. I would have, yeah, I was 31 by the time that finished. No, way more than that. How old am I? Oh, 2014 to 2018. I was 35. Yeah, no, that's good. Yeah, very good. Yeah, yeah. So does that answer your question? Most PhD programs will give you a stipend that if you know about it ahead of time, research thoroughly, live with roommates, and eat beans, you can live on. And then postdocs, similar, but it varies a lot by location. It's completely underpaid, but you'll have to have roommates until you're done being a postdoc. Very, very likely. Probably quite a few. Sorry? I mean, that was extreme, but $400 in downtown DC, like it's crazy. It's crazy. It's unbelievable. For $400, I'll deal with mice. I killed a lot of mice. Like I had traps. But what are you gonna do? They eat my fucking food. Okay, we're done. I got in trouble with the tenure committee for swearing in class. More questions? Okay. You know what? While we're sort of on theme, I guess I will aim to be done in maybe. Okay. Let me jump to point number 3 a little bit because we're sort of on the we're in the meta, right? So let me jump to point number 3, and then I'll gesticulate about point number 3, about number 2. So this is sort of a laundry list of fairly standard things, but and to be honest, like I've already mentioned mental health, like figuring out how to exist in this field in a brain that doesn't scream all the time is very important, and you should devote time and resources to figuring that out. It's not trivial. Okay. I've already said try to understand. So the sort of very, very brutally practical tip is don't be picky with your undergrad research. I've been on the grad admissions committee for the last 4-ish years. What's really, really impressive, like, let me put it this way. When I look at people, and I'm in particle theory, so let me think about this as a particle theorist, right? If I have 2 applications in front of me, and they both do good advanced courses, whatever, they have all the math and all the things you need, okay? Core theory and M, whatever, okay? None of them have quantum field theory, any of those things that I might care about, but they're all solid. One of them did a summer research project with a particle theorist and did some simple calculation, and the letter is like, fine. The other one did a completely random research project, I don't know, biophysics of bees, like literally anything, but they just fucking smashed it. Like the letter is 3 pages, the PI is like, oh, this guy was so great. Oh, they went into the field, there was a problem, they just did data analysis, they researched this. It is completely irrelevant what your research project is, but if you ultra impress your prof and they write you that letter that goes, yeah, that is 1,000,000 times better than relevant research experience. That is a really important practical tip. In many fields that are, especially if they're cool and shiny, like particle theory or astro with all the nice pictures or whatever, right? Research opportunities are very limited. Go do anything. It does not matter if it's your final field, but whatever it is, you treat your project with the respect and the absolute dedication that will wow the fuck out of your prof, and then they will write you a scintillating letter, and that's going to be worth way more than, you hope you win the lottery and get a whatever project in your research area, and then it's 2 months of some little calculation, who cares, right? Like, that's a really, really important practical point. Don't be picky with your research, but impress the person, do a really amazing job, and be independent. And the other stuff is what I've already said somewhere, like these ephemeral qualities, like you got to know why you do what you do. And this includes your undergrad research, right? Respect the project enough to ask, why am I doing what I'm doing at every level of this complexity, right? It'll allow you to truly understand what's happening. because research skills are very universal, surprisingly. The technical skills aren't universal, but research skills are universal. And as I've spent more time being faculty, I've really appreciated the huge difference. It's possible for students to be academically brilliant and absolutely suck at research, and vice versa. The two are correlated, of course, right? It's very, very unlikely to get a GPA F student who like wows you at research. They are very correlated. But once you get to like the top-ish level, I've had like, it is very possible to be okay academically and an absolute research star and vice versa, okay? So wow your PI, and it roughly doesn't matter what it is, okay? Get something on, if you want to go to grad school, if you want to go to industry, why are you talking to me, okay? I have nothing of value to add. I mean, work hard on your courses, mental health, understand why you're doing what you're doing, okay, fine. So, but that's the main practical one. Any questions before we move on to whatever research tickles my fancy these days?
Just a little quick question. Like when applying for grad school, how important is it to have done grad courses?
It helps, but a 4.0 GPA without grad courses is better than a 3.5 with. Not to make anyone feel bad who fills those exact numbers, but I'm making up these numbers, but you get the point, right? Like, you will do grad courses in grad school, right? More questions? Okay. Obviously, if you think of a question about a different topic, ask at any time. For what it's worth, I'm going to talk very briefly about some really fun current research that I'm doing, just as a palate cleanser. So the broad area is complex dark sectors. So what is that? As a particle theorist, I'm motivated by, as a particle theorist who is quote unquote a phenomenologist, which means that I care about particle theory that, broadly speaking, is in any way, shape, or form experimentally relevant between now and 200 years from now. Okay? So I don't do quantum gravity, I don't do string theory, I don't deal with the cosmological constant problem for the most part. I do worry about every other part of particle theory, most importantly, the shortcomings of the standard model of particle theory. So the hierarchy problem is a really nice one, so let me mention it very, very briefly. The hierarchy problem refers to the Higgs boson. Now, when you write down a Lagrangian, which is the thing that encodes the laws of the universe, those of you who are third year and above know what that is, but don't worry if you don't. Lagrangians are built up and governed by symmetries. So the point is that, so very concretely, the standard model of particle physics has what we call a scalar field. It is a particle without shape, right? The photon has a shape, it has a polarization, right? It can be this way or that way. The electron has a shape, it has a spin. If you put it in the magnetic field, it will go blink, 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 right? These particles have shapes. They have non-zero Lorentz representation, right? Spin half, spin one. The Higgs boson is a field without shape. It has zero spin, it has zero charge, it has zero anything. It is a completely inert particle. It has couplings to other things because it originates from theory and so on, but as a sort of like entity, it is a true point particle in the like smooth sense of the word, okay? That smoothness has important consequences. It's the most symmetric particle there is, right? We know it exists, we've discovered it. Even before we discovered it, we knew that it or something like it had to exist for the consistency of the standard model. But the Higgs boson has a problem, and that's the following. So when you write down terms in the Lagrangian, the mass term of the Higgs looks like this. So it's just the mass of the Higgs squared and then the Higgs squared itself. Okay, don't worry about the rest. But the thing about the Higgs is because it's so smooth in that mathematical sense, this thing has no symmetry features, no symmetry restrictions. If I put, photons, for example, or electrons or whatever, they have features. I can't just write down any mass term I want, okay? The Higgs boson, I can write this mass term, there's no symmetry restriction of any kind, and more to the point, this thing can have a priori any value, but whatever, I measure the value I measure. But it turns out, if I think of this being time, that the Higgs boson interacts with every particle that exists in the quote-unquote spectrum. So what I mean by the spectrum is we have electrons. Electrons are in the spectrum of my theory, which means I can make them. Yeah. Right here, there is currently not an electron, but the spectrum of the theory contains an electron, right? So whether or not a particle is here right now, in the room with us, it is in the spectrum, okay? And which particles are in the spectrum is what constitutes the fundamental laws of the universe, right? What is the particle content of the Lagrangian? What is the field content of the Lagrangian? But whatever is in the spectrum, vacuum fluctuations of that thing will talk to the Higgs boson. And because there's no symmetry that restricts this number will just be the maximum mass scale that exists in the field, in the theory, squared up to various factors in front. There's no symmetry that restricts it, so the Higgs couples to the vacuum at all energy scales, at all mass scales. Everything that exists talks to the Higgs, which means that you would expect its mass to be at the Planck scale. Because gravity has a scale, it's the Planck mass. That is the energy at which gravity becomes strong interacting, at which you form black holes microscopically, and blah, 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 yeah? So you'd expect this to be the Planck scale. M Planck squared is 10 to the 36 GeV squared. The actual mass squared of the Higgs is 10 to the 4 GeV squared. So in order for this quantum correction, which you have every reason to believe exists from the deep principles of quantum field theory, in order for that to end up as this, you have to add a constant, which cancels down to this, which means it's a constant which means that the vacuum and all its various fields and all the various beautiful complexity of the universe, all of it talks to the Higgs via these quantum loops. You get some insane number that is some number in front times 10 to the 36. And there is this number that has no dynamical origin. It's just a thing that pops into the theory. And it's the same as this crazy set of dynamical processes to 32 decimal points. To cancel down from 10 to the 36, which is a trillion, whatever, to 1,000. That's called fine-tuning. And it's insane that the universe does this. In fact, it seems very likely that it doesn't do this. I would say, and many people would say, the Higgs is secretly symmetric. It's not obvious today because it's very easy. Think of a magnet. If I take a piece of iron and I heat it up, it's all random inside, and that's a very symmetric state. But if I cool it down, the atom spins a line, I have a magnetic field now establishing itself, and I have broken rotational symmetry because I've picked the preferred direction. So the ferromagnet that was hot gets cooled down below the transition temperature, it breaks rotational symmetry. It is possible for the ground state of a theory, the low energy state of the system, the cold lump of iron, to break symmetries that the fundamental laws that make up the system fundamentally obey. The physics that governs the iron is rotationally symmetric. The system that is the iron at low energies breaks the symmetry. Very standard, no problem. So you can imagine. So the postulate is that the Higgs is secretly symmetric, and that the symmetry means that this doesn't actually happen, and therefore this tuning isn't there. The most canonical example of this kind of cancellation is called supersymmetry. You may have heard about it. Even if you don't know what it is, it's a very common thing to hear in pop sci or whatever. Supersymmetry, spoken very colloquially, is an extension of the standard model that introduces the symmetry. It solves the hierarchy problem, but it has the side effect, this symmetry, whenever you introduce a new symmetry, you introduce a new symmetry. Whenever you introduce a new symmetry, that symmetry has requirements on the Lagrangian. Your Lagrangian now has to be symmetric under it. Supersymmetry requires that the Higgs boson in every other particle has a superpartner, a different kind of field. It could be heavy enough we can't see it, but the mass cannot be much heavier than the Higgs mass. In particular, all the matter that we're made of, quarks, whatever, have these superpartners. They're called quarks. And the Large Hadron Collider was built in part to make them because supersymmetry predicts that all the quarks get copied to squarks, but just like quarks, they're still active under the strong nuclear force, and because the Large Hadron Collider smashes protons, it's a strong nuclear force smash collider. So strong nuclear force goes smash, and out should be coming the squarks, and they have not. And they have not for a while. We kind of expected squarks at the Large Electron Positron Collider at CERN in the 80s and early 90s, and they didn't, and it was like, our estimates were off. It's fine. It's fine. Guys, so the lab should have found squarks at the 100 GeV scale, didn't find them. It's like, this is fine. What's the factor of pi among friends? And that's true. That is okay. But then the Tevatron, active in Chicago in the 90s, discovered the top quark in 1996. It had the energy to discover 400 GeV scale quarks, and that's kind of where it should be if everything was really natural and supersymmetry. And again, didn't find any in, and then why should nature? 4 pi is good. Let's do 4 pi. Stops could be 1.2 TeV, 1.2 thousand proton masses, and the end still, the LHC has not found them. So on the one hand, you have a really, really deep mystery of nature, which is the hierarchy problem. It comes out of the most rigorous confines of quantum field theory, and it presents you with an insane universe. And like if you're like of the like sufficiently nihilistic complexion to like stare into that and be like, that's fine, like that's okay, you're done, you don't have to do this. But if you think that tuning to 32 decimal points is fundamentally disturbing, then you say, I want there to be a dynamical explanation. Supersymmetry is great, and various versions of it. There's other things that do roughly the same thing. But they all predict these extra particles, and they all have to be not much heavier than the Higgs, 4 pi, yeah? And, if we're really pushing it, and they haven't been found. In the last 10, 15 years, there has been a shift in the way the theory community thinks about these things. We have realized that, as with many things during the 90s and 2000s and way further back, we were maybe a little bit arrogant and a little bit narrow-minded about how we think these things should play out. And in their defense, this arrogance has a defensible reason. Because in the 60s and 70s, people wrote down the standard model, and they were like, there should be a bottom quark and a top quark and a charm quark and a W boson and a Z boson and the Higgs, and they should have roughly this mass, and we're going to calculate hyperfine corrections to pion decays and whatever, and therefore the B quark should have a mass of roughly 5 GeV, and the top quark should be above 100 GeV. All of it was true. The entire particle content of the standard model was predicted in the 70s, and for the next 30 years, it was just fucking success after success after success, discovering them. What does that do to you? Like, as a person, when you just like, and then for the next 30 years, humanity's mega projects confirm your idea to the decimal point. I would be getting pretty sure of myself. So particle theorists, for the most part, got bored of the standard model, in the 70s. I mean, that's completely untrue. Like, there was lots of work to be done. But like, in terms of like finding new theories, finding new symmetries, like the standard model was written in the 70s, and it's correct, it's written in the 70s. It's really fucking frustrating. And then, so they write new things. So let's work on string theory. Let's work on supersymmetry. Let's work on all these things. And the same kind of thinking that gave you the standard model is what led to the assumption that supersymmetry is obviously out there. And obviously there's, squarks or whatever at 500 GeV. And with that perspective, you kind of get it, right? Like, they thought that human intuition was just so pure and so excellent, a spear in the hand of the sun. And like, of course it would just work, yeah? And then it ultra didn't for like 20 years. And then I remember distinctly in 2015 or so, a lot of the older generation theorists were like very sad that we discovered the Higgs and nothing else, and everyone was moping and depressed. And then all the young theorists were like, this is amazing. All those old guys were wrong. This is great. But they weren't wrong in a way where they're idiots, right? They were wrong in a way where nature is more interesting than we thought it was. And over the next several years, what became clear started becoming clear, the first of these papers came in 2006 by Chaco and friends. But then there was a lot of work on it, and I did a lot of work on it in the 2010s and still today and so on. There's theories called neutral naturalness, where basically the same deep symmetry principles that solve all of this are still in the theory. But the exact way in which the details of the theory completely change how it looks today. And it turns out, and this is not contrived, the details of the theory, in the UV, it's supersymmetry, whatever. In high energy, small distances, it's supersymmetry. It's all those respected, excellent, brilliant old ideas, okay? But once you think about it with an open mind, with a maximally generalist, maximally non-arrogant perspective, you kind of realize, like, oh, if I write down these terms instead of those terms, supersymmetry doesn't tell me not to do that. But then I end up not with a bunch of new particles that are charged under the strong force at the LHC. I end up with a copy of the standard model that is in the dark sector. I end up with dark electrons, dark protons, dark nuclear forces, dark photons. And there's a discrete symmetry between them that swaps the fields. And that discrete symmetry is sort of kinda what is bridging the gap and helping you solve the hierarchy problem. It is a sort of like a non-trivial manifestation of these deeper principles. The UV principle is still the same, but the manifestation in the IR, in our world, is such that there is no supersymmetry at the LHC, but dark matter is much, much, much more interesting than we ever imagined. And that motivates us thinking about dark matter candidates that have complex self-interactions, dark matter candidates that have dark atoms and dark photons, that form dark stars, that have dark galactic Milky Way disks. All these things are hypothetical, but deeply theoretically motivated, but they are really, really hard to understand what they do in the universe, because the universe is complicated enough as it is. Now imagine some alternative universe fan fiction version of it that's actually dark matter that's also there. So we have to learn more astrophysics to look for this stuff. So that's what I'm doing a lot of my time, and it's super exciting, I think. And maybe it'll take us 30 years to figure out how to do this correctly, and then we find it then. But that's kind of it. Yeah, question. I mean, some, but most importantly, I would say, well, some, but you need to know particle physics too. Depends. Yeah. More questions?
Actually, but if the Higgs were actually at that
No. Oh, sorry. The question was, if the Higgs was at the Planck mass, wouldn't that cause unitarity problems? Sorry, good. You, sir, are a plant. Okay, Mr. Know-it-all. Yes, indeed. Given the observed W and Z boson masses of about 80 and 90 GeV, it would violate unitarity to not have a Higgs below 170 GeV or something like that. But a Higgs with a universe with a Planck. So that's why we knew the hierarchy problem was a problem before we discovered the Higgs. Right? The point is, a universe with a Planck scale Higgs still works fine. There's no reason for the Higgs to be that light. And yet it is. More questions? If they're technical, let's talk later, but more questions. Okay, Q&A? Or did we have a Q&A? What's going on?
I think we do have a Q&A. I guess one round of applause for our speaker. I guess I will stop